A very good morning to you all and a warm welcome to a free webinar on optimizing golf course safety net design using data-driven trajectory analysis and 3D modeling. A collaborative effort between Structural Design Institute, formerly known as SDI, and our esteemed partner, Civil and Structural Engineering Consortium Private Limited. If this is your first time with us, SDI is an educational institution that has a lot in store for you. We specialize in engineering covering areas such as design, construction, and software training. What sets us apart is our close affiliation with civil and structural engineering consultants, a name synonymous with excellence in the field, having worked on several iconic projects in Sri Lanka. At STI, we are committed to the continuous professional development of engineers. So we offer CPD courses and events for those pursuing chartership or looking to enhance their skills. You can see a few of our ongoing and upcoming courses here. We are focused on structural analysis and design, architectural modeling, and even some courses focused on specialist topics. What sets us apart from other similar organizations is our exceptional faculty, as our educators are all practicing engineers with extensive real-world experiences, and some of whom are even renowned in academia. We also offer a set of publications, including tall building guidelines for Sri Lanka and construction specifications for tall buildings in Sri Lanka, as shown on the screen, with more to come. These books encapsulate our team's wealth of experience, diving deep into design and construction specifics. Today's webinar, the first in our series for the new year, 2026, we have optimizing golf course safety net design using data-driven trajectory analysis and 3D modeling webinar focused on the advanced engineering methodologies used to enhance safety in golf course environments. This insightful session will explore the analytical, structural, and technological aspects of safety net design, including ball trajectory modeling, data-driven height optimization, spatial analysis, and the application of 3D modeling tools to achieve efficient and reliable solutions. It is a valuable opportunity for both aspiring and practicing engineers, as well as professionals involved in sports, infrastructure, and facility planning, to deepen their understanding of modern technology-driven design approaches that improve safety, performance, and overall project effectiveness. So before we start today's webinar, let me quickly run through a few housekeeping points to make sure today's session goes smooth. First, if you have any questions during the presentation, please type them into the YouTube live chat. We'll be monitoring the chat and directing your questions to the resource person, and all these questions submitted will be addressed during the Q&A session at the end. Secondly, a certificate of participation will be awarded to all attendees who complete the attendance form. The link to the form is available in the description of this YouTube live video, and we also share it again in the live chat when it is open. So now this is important. The attendance form is not open yet. The attendance form is not open yet, and this form is currently not open and will only become accessible once we announce it during the webinar in the YouTube live chat. So please keep an eye on the live chat for that notification. Once the form is open, it will only remain open for 20 minutes. So please make sure to fill out within that time if you wish to receive the attendance certificate. If you experience any issues while trying to submit the form, kindly take a screenshot of the problem and send it to us via email or WhatsApp. Please note that we will not be able to answer phone calls during the session, so messaging is preferred for any assistance. With this, let's begin today's webinar. It is with great pleasure that I introduce our distinguished speakers for today's webinar. First, we have Engineer Air Vice Marshal Udula Vijayasinghe. Engineer Udula is a distinguished professional with extensive experience in construction project supervision and project management in Sri Lanka's building and infrastructure sector. And engineer Udula Vijayasinghe, Vice Marshal Udula Vijayasinghe joined the Sri Lankan Air Force in 1990 and was commissioned as pilot officer in the civil engineering branch in 1992. He has had several key positions, including Director General Construction Engineering in the Air Force, overseeing critical infrastructure projects. A chartered civil engineer and a graduate of General Sir John Pathelawala Defence University, Mr. Vijayasinghe's 32 years of distinguished service earned him numerous awards and commendations for excellence. Today, he is serving as COO of CSEC and bringing unparalleled leadership to our operations. To say why he is the best match for this webinar related to golf, he is a golfer who has many achievements under his belt, being the winner of January Monkey Medal at RCGC and winner of Turkish Airlines Golf Tournament, and went on to participate in the Turkish Airlines World Golf Cup Grand Finals. So with that, we are honored to have Engineer Udula with us, and we look forward to an insightful discussion powered by his rich experience in these related sectors. So without taking much time, I would now like to hand over the controls to Engineer Udula to conduct today's session.
Thank you very much, Andrea, for the nice introduction. Once again, good evening to you all. Today, we are going to discuss very important matter. As a practicing engineer, you should know these things. Today's webinar is optimizing golf course safety net design using data-driven trajectory analysis and 3D model. So, ladies and gentlemen, this webinar consists of two parts. The first part will be introduction and information, and design approach part will be covered by me. And the second part will be modeling and analysis part, and it will be covered by engineer Kemil with the practical examples. The table of contents of our webinar as flashed on the screen. The first part, different mode of engineer engagement or problem. What is golf? Why is this popular? Golf population by skill level, type of clubs, golf ball explained. Then the analysis and the modeling part, location, work plan, survey, then the data validation, summary of results in the 3D interpretations. So without taking much time, we'll move into the first part of the webinar, the information and introduction part. So, ladies and gentlemen, for this requirement, I would like to give a hypothetical example for you all. For a moment, just think about a person want to build a house. So hereafter, I'll tell the person called client. So one client want to build a house, maybe 3-story, 4-story. So with this requirement, he may or she think, okay, my house should consist with 5 bedrooms, then rooftop swimming pool, basement garage. So with that thing, he may think about some kind of images in his mind. But up to certain extent, he can't go further. He needs someone's assistance. So then he or she has to hire an architect. So the architect will discuss with the client, and they will finalize some kind of drawing with the dimensions. So we call architectural concept or architectural layout, basic. But still they can't build a house. Why? They need some structural advice from you all. So then that part will be given to you. Then you will do your part as a structural engineer. Maybe you calculate what bending moment, shear force, axial forces, or load compression, so on. And you will give the most economical, viable design to the client. So accordingly, the client will give to the builder or contractor to execute the construction work. So that is the one mode of engineers engagement in as a structural engineers. You are getting this type of issue. The other issue is more relevant to the today's topic. So here the client will directly transfer his problem to you. There's no architectural environment in here, but client will give the problem to you. As a practicing civil engineers or structural engineers, you have to sort out the client issue now. This is somewhat difficult and completely different from the first engagement. So here I would like to give not the example, the actual thing. About 3-4 months back, the Royal Colombo Golf Club captain and the committee members invited the civil and structural engineering consultancy private limited deputy chairman engineer Shiromal Fernando to sort out the issue. So as I remember, Mr. Shiromal, Kemil and myself went there to discuss the issue at the Royal Colombo Golf Club. Then they explained the issue is the golf ball will go out of their perimeter and it will go and land in somewhere else for others landers, neighbors landers, lands. Then it will damage the properties, vehicles, sometimes people. So there's a big issue for the golf club. Even the neighbors are going to take legal action against the club. So then we ask, what is your right? Okay, what is your solution? So obviously we can see even safety nets are there. So then we said, okay, if you can give the safety net dimensions and the height and other things, we can do a structural design for that. Then only they said, no, that is the issue. We have put several nets up to several heights, but still ball is going out of the perimeter and the fairway. Then we thought, so right, now we have to address this issue in different way. In that case, we came to our office and we studied this situation. So for the easy understanding of the modeling and the analysis part, you should have some kind of idea about the golf. I know most of the people know this the game, but to refresh your mind and easy understanding, I would like to cover certain things relevant to the golf. What is golf? Actually, this sports originated in 15th century in Scotland, and this is club and ball sport. Objective to hit the ball into the hole with least amount of shots. If you can complete the one hole with the minimum shots, you can get more points, something like that. So I am explaining in a very simple manner, not the exact thing in the golf course, but that is a bit complicated. So score is the total amount of swing taken to reach the hole. So there is a word called par, average swing taken for each hole expected to be taken by an expert player. That is, the expert player means the minimum of errors he made, not like others. So handicap. So this is numerical measure of the golfer's average performance above par. That means if you are a good golfer, you get the low handicap. Your mistakes are very limited. If you are a middle level, the middle handicap. If the errors are more, then you are coming to the higher handicap level. So this is a very nice saying. According to Jack Nicklaus, the famous golfer, the golf is 90% mental and 10% physical. So when you're playing golf, 90% mental, and not like other sports, you can't complain about anything else because you are the one who are going to keep the ball and swing. The other sport, you can say even for an example, cricket, you can say that the ball has the more swing and more speed, so I unable to play like that. In here, no, the static ball, you keep the ball, you select the club, you select the other factors like winds, the trajectory, draft angle, everything, and you say, then you can't complain anyone else because you play against you. Another thing is it is impossible to repeat the exact shot even in your life. There's no second similar shot in your life. So 90% mental and impossible to repeat an exact shot every again. So you can, as engineers, you can see the variables to be considered. It's not that easy. So why golf is popular? Played over all age groups, low impact sports can be played for life, social benefits, builds for face for interactions, then professional benefits, golf for networking, sports, bring people to various parts as flash on screen. You can see these things, and even you can see even the 5 years old people, the children play golf, and also 3 years people also age of people also play the golf. So until you die, you can play if you are physically fit. So this is also another important information, the population by skill level. At the moment, according to the statistic, about 190 million people play golf worldwide. Very high margin for errors if not in the perfect mindset. As I explained, this mind contribution is about 90%, and you can see the skill level. Only scratch for better golfers, only 1%. Low handicappers, that is 0.5 to 5%, only 5%. Mid handicappers, 32%. High handicappers, 62%. So 111 people coming under the mid handicap or higher level. So you can see the errors. When they play the ball will go here and there. The accuracy is only 1% can play the accurate golf. These are the type of clubs. Generally, we call drivers, iron, hybrid, wedges, putters. So drivers being the long club, then you can hit long distance. Accordingly, other clubs you can hit several distance. And the putters call when you are playing the golf, the green you use that putter. That is for your just for your information. And now you can see the club carry distance. So driver generally you can hit about 250 meters or yards, more than that. So stretch golfers they hit about 270. So PGA Tour players 300 plus sometimes, but for the competitions even 450, 500 some people hit half a kilometer. So when you play the driver, you can see the accuracy. The lower handicap have tighter range of the angular difference, and being 65% 3 million people will play away from the fairway. According to our statistic, you can see about 65 million people will play out of the fairway. So it will go to the neighbor's place, obviously. So that is the issue. This is another important information, especially for better golfer. Fairway, they keep the 56%, 0.5, they will keep the ball in the fairways between the golf course lines. The lower handicap 51, so less than the 42%. Accordingly, their distance also 360 to 275. So on. So this is the golf ball explained. You can see the golf ball. Lot of dimples are there. You can just pass it to the audience. And with that, dimples, you can reduce the drag force. The first picture we explained, you can see the airflow and the drag force, the height of the drag force. And with dimples, you can reduce about 50% drag force. Generally, 300, 500 dimples are in the golf ball. So this is another important experience, spin. So we call the revolution per minute. The ball will spin. You can see the on particular video. And generally, if you have more spin, then your ball will go here and there, due to the forces applied. Right? If you have a low spin, you can play straight shots. So you can say that even Tiger Woods and Rory, they are spin level to 2,200, 2,500, but amateurs they play 3,000 plus, 2,500 plus. So this is ball path. This is a summarized ball path. You can see about 9 parts, right? I'm not going to explain all the details. You can say the straight shots and slides. Slides means to go. You can refer that table and the chart. Another one is draw. So you can see the missed shots. That's going to the out of the air and ball into the water. That is we call hook. Draw and hook. Ball will go not straight. This is fade those slides. See, he's trying to aim that particular the fairway, but it will go to the right side of the fairway, and it will go and land it in somewhere else. So when you compare the speed of the ball, you can see this compared to the other sports, except badminton, the shuttlecock. The golf ball speed is about more than 175 miles per hour. And the weight of the golf ball may be around 46 gram, and diameter may be about 43 millimeters. So you can imagine the impact and the momentum of that ball, not like shuttlecock, though it's a better speed. So this is a compound of a golf course. Every international level golf course, standard golf course, you will get 18 holes. You have to play 18 holes. 18, that means 18 fairways. So with the scarcity of land, they will locate the fairways like this, zigzag format. And if you go think about the 14th fairway, adjoining into the perimeter of that particular land. If you hit in from the 14th fairway and if you go to the left side, the ball will end up in the neighbor's land, and it is a problem against the golf club. So this is a component of a golf club. When you go to the golf club, you can see the tee box, that is the starting point, and you can see the hole. So you are playing from the tee box to the hole with the minimum number of shots. Then you will get some kind of obstacles, the rough surface, then the bunker, that man-made thing, the sand bunkers, ball will go to the sand bunkers. It is very difficult to get out from the bunker. So we have to have a special kind of techniques. And other thing is the tee box, then rough bunkers and all. And the during the it's up to the green, you can see the pin and the hole, and around the green also sometimes you may get the bunkers. So with that introduction part, I would like to hand over to Engineer Kemil to for the second part of the webinar. Emil, over to you.
Thank you, Engineer Ulla, for that very descriptive session on the botnets and related information. And with that, we will move on to our second speaker, who is the engineer Camille Peter, who is a civil engineer with over 3 years of experience in Sri Lankan building infrastructure and the building sector. So he's currently attached to the civil and structural engineering consultants, where he's primarily involved in project management and coordination of engineering projects. So with this strong foundation to civil engineering and hands-on experience to project execution, Engineer Camille contributes to effective planning, team coordination, and successful project delivery. And he also not only delivers those aspects, but also deliver these kinds of analysis and modeling when it is required for the project. So the analysis and modeling for this project was conducted by Engineer Camille, and he will move on to explain more about how this was done. So over to you.
Thank you, Andrea. Thank you, Mr. Ulla, for that very descriptive introduction. I think now everyone has an idea of what we are getting into and what we have to consider mainly. So just to start off, recapping on our problem. So this is the location that we had to deal with. So this is the golf club. And as you can see, the highlighted area is the area that we were concerned with. And you can see that, now Mr. Ulla spoke about the tee box. And after that, where your green is. So when we start at the bottom left is where your tee box is. The small curve that's kind of sticking out. And then if you have to look at it more directly, so you see the red line is the path that people are aiming to get. So the problem here is the property also has a kind of curve inward and then goes out. So given the sport objective and the land layout, it was a bit of a challenge, and that's where these people have this problem of where the balls keep getting into the private lands, right? So then once you visited the site, these are a few photos from the site. There are 2 tee boxes. That is where you start off with. The one on the left is the one that's further back, and one on the right is the one that's up in front. So you can see the netting that is already there. There's a 15-meter net, and a bit closer, the 12-meter net. The height is less, but then because it's closer, it gives more protection closer there. But the back, you can see that there is no specific protection anywhere close by. The only nets are the nets that are found in front. So just to visualize the kind of shot that you'll be playing, these red color lines are there to kind of show you what the people, mainly when the players play, this is the target that they go for in order to get to that 14 green. So when we came up with this problem, so we had to kind of figure out how we're going to do this. And this sequence that we followed, we went off with a 3-dimensional survey. Then we had to do some modeling as well to kind of figure out how the ball travels. And then after that, interpreting the results and giving a proposal to the people. So first step was conducting the survey. Now as engineers, civil engineers, I know we are all, this is not something new to us, right? Any site that we visit, there is going to be an initial survey that is done. Usually you will do it using your normal equipment, you'll get to station, a PL, or there will be some traversing that is done in order to do this, right? But the challenges that we have to face here is because, okay, in the terrain-based modeling area, that would be possible. But we have problems with the amount of time that it's going to take, with the amount of people that it's going to take, the manpower that is involved. And this is a big environment. There are trees, there's a net, and we have practical problems of how we're going to reach the height of 15 to 20 meters with either people or equipment in order to get the exact data. So with that, what we opted for is to do a 3D survey. So to do this 3D survey, they use drones, right? And there are 2 new methods of surveying that is used. Usually what we have heard of is LiDAR surveying. LiDAR surveying is usually done using laser technology. So this is similar to that, but it is using photographs. Yeah, so the drone will take multiple photographs which are also geotagged, right? And they have another feature that they use called RTK. So in our phones and everything, our GPS receivers usually have accuracy only to the nearest meter. So what the RTK does is it helps us to get more accurate and give us centimeter level precision. So given our application here, this was more than suitable and it's really fitting, to our requirements as well. This is the procedure that was followed. And if you can see the first step I mentioned, I said the input of a KML file. That is basically the first slide that I showed you, a small polygon drawn on Google Earth. Basically, you go on Google Earth, then you kind of look to where you want to do your survey, you mark out the area, and then you provide it. And then after that, you have to go for the relevant authority approvals. As you know, drone flying and everything, there is a proper regulation that is used. There will be a supervisor that will follow you on site on the day of inspection as well. And after that, there is a flight path that the drone will plot. We will get into that as well, and then we collect our data. So this is how the survey was done. You see the first picture on the left. That is the area highlighted is what we needed to cover. And then the lines in green, basically when we input this data saying that we need to do this survey into the drone, then they will give a proposed path. So they will say, okay, this is the path that the drone is going to fly in. Basically, almost everything is automated. And then in the second one, you can see we make small adjustments because there are concerns with the approvals that you have. If we got the approval from the golf club, it doesn't mean that we have approval to fly over private areas. So there was a small concern there where it kind of reaches a bit out of your territory that you want to do your surveying for. So we had a discussion with the person who was there from the relevant authority to give us the approval, and then he said, okay, it's going to be a quick flight, so you need to reduce it as much as possible, and then only we proceeded. And on the third image, you can see, so in order to get accurate, they will take 2 reference points. So they will take GPS coordinates in 2 known locations, and they will keep this so that they can calibrate the data after they get the drone results. And these are a few videos actually of during the drone taking process. As you can see, the drone flying there on the side, you can see the path that it's following. And on the bottom right, you can see the drone camera so that if there is any obstruction, the pilot can actually see in case of any trees or anything that he doesn't run into that as well. Another feature is when it's doing all of this is automated. So the drone is just automatically running on that path once you give the input. And they also have a set height that they keep above the terrain. So in case you have, suddenly going into a mountain area or something like that, drone will automatically adjust and increase its height so that it keeps that same gap from the. And then this is the results that we got from the survey. So what they did is they will basically, after collecting all the data, then there is obviously software that is used to kind of compile all of it. And what they gave us is basically just a internet link, right? So this is CCM Ion. So this is a software actually that is cloud-based. It's a 3D geospatial software. So it's like any other geospatial software we use, but the backend operations obviously being somewhere else. You can basically access it on your computer, on Chrome, and then use it and manipulate it as you wish to take measurements, to take heights, angles, distances, anything you wish to. So this really helped us get over, the challenge of how we are going to take the measurements, what we need, what distances, and all of that. Next, predicting the ball path. Now we have done a survey. Now we have the existing conditions. Next thing is what we have to consider. Okay, now if you take a golf ball, how is it going to travel? What do you need to consider? What is the main things that will make the ball path change? So we needed to do some studies into the ball path. These are the main factors that we identify, right? So when you're basically predicting in the model, what you're trying to do is do a ball filter like those lines, basically figure out what kind of line is the ball going to follow. So we needed to know about the speeds. We needed to know about the angle when the ball is hit. And then we also needed to know how much a spin is going to apply because during that ball traveling, it's going to sway because of the spin. Next, we needed to know basic stuff like launch direction. And also we have our wind speed, atmospheric pressure, even those kind of things actually affect the ball path. And while doing this, so luckily we were able to come across during our research, there is a model that has been developed by the University of Illinois. So they have actually prepared one model where they can predict the ball path, and they have also considered this is not like a basic trajectory modeling. There is a bit more detail that needs to be considered, like the lift, the drag based on the ball properties. So there has been a lot of intensive research done. The Washington University also has done some studies about the drag and lift coefficients. All of this has been applied, and they have an Excel available that is usable to the public on their link. So with that advantage as well, we took this and then we tried to see how we can use this in our application as well. So this is kind of the trajectory that you would see, and the side on the right side you can see the ones in yellow and blue. Basically, those are our input items. And then getting into the parameters. So now, given all that, the introduction that Mr. Udula said as well, that the statistics are going to be what you can count on, because it's like a weather. You can't really say, okay, this is what's going to happen, but then how you do it, if there is some unpredictability, is you use statistics. The same way we also apply statistics, try and see what kind of probability there is that these kind of situations will happen. So we had to also assess everyone from the pros all the way down to the amateurs to see what kind of factors are important. And as you can imagine, obviously ball speeds, the better you got, only even the higher speeds that we can get. So when we are referring to the 95th percentile, we are only looking at the top 5% people from each category. So these are the speeds that only the top 5% probably can achieve, right? And then we looked at the bottom ones as well, because as we go on in other parameters, the lower ones actually mattered more. In terms of launch angle, as you can see, so with the low handicap actually keeps it more sharper. Usually an efficient angle that was seen to be for launch angles was between 10 and 16 degrees. So anything more than that or anything even less than that is not going to give you enough ball carry. There are a lot of factors that affect it, obviously, but these are the stats that we're looking at. But as you can imagine, obviously, the more error people are trying to get that angle, but will end up having a misfit and maybe getting a bigger angle on their release. Also, the spin, as we spoke of before, we are talking about different spin rates. Here, what we have considered or what we have put as 3000 is because also, although the spin rates increase, the intensity of the ball hit, the ball speed, and everything makes sure result in a very small ball drop. So because of that, it was found to be not as significant. And because of that, we had to kind of stick to an average value here. Otherwise, the variability was very high. And then these are the weather parameters that have been considered. Given that it's Colombo, we have got high lows and averages as well. Next step was to figure out now we have what our parameters are going to be. Now we need to kind of see the sensitivity. If you change your speed a lot, how is it going to impact? If you change your spin a lot, how does it impact? Does it change the height? Does it change the distance, the range, and everything? So we did some sensitivity testing. Here you can see how the ball traveling arc changed with the different speeds. And as you can see, that is the existing net that was there. Next, we get into the launch angle. So while we are changing the launch angle, we also kept the other items the same as one median level. And then after that, we would change the launch angle to figure out what is happening. Here you can see how the launch angle gradually increased up to 20 degrees. Now you can see why the players actually don't opt to go for anything more than 20 degrees, because the higher the angle you go, the ball doesn't carry as far. So it's no point for them. So they want to get maximum distance, right? So everyone is targeting to keep it low. But then the probability that more than 20 degrees can happen is something that we have to consider. Next, we'll look at the spin rate. Also, we'll go to the graph. I think will give you a better idea. Yes. So the spin as well, as you can see, for 1000 RPM, it goes a certain distance. And then 1500, a bit more. For 2000, actually only it's the optimum spin. Optimum reach is there for 2000. Anything above 2000, again, the height that it travels reduces, right? But then the peak height increases, as you can see. So we had to consider up to about 3000 because the peak height was increased. And we need to intercept the ball at an early stage because it was more feasible than trying to intercept it at a high peak. Now, the next step was, okay, we have all this data, now we are using a model, but then how accurate is it? Right? We have this question on whether this actually gives us a real-time comparison or is it just a random Excel that gives us some values? So in order to do that, we actually had one person participate, and the best thing that we could get close to a real-time data was using a software, a simulator. So there's a TrackMan simulator that is what golfers use. That is something that they can use at home or even they have actually at the golf club. So they use this to kind of see their statistics, how they hit the ball, how hard they hit it, and the kind of values that we were talking about on their real-time shots, they can actually get it checked. So we had some sensitivity testing done. This is the interface that is there. So it kind of tells you each of his shots. It will give you the speeds, the spin, and all the factors that will matter for them. So when they need to make the adjustments, they will look at this and know what angle they committed with. As you can see on the right side, you can see how the ball changes when your angle face is there and all of this. And the ones that I've highlighted are the key factors that we observe. These were on the top, you can see top left, that was the highest speed that was recorded down one of these shots, 172 miles per hour. And then on the top right, you can see the spin. This was a miss hit that he got. The speed isn't as much, but then he went up to a spin of about 3,508. And then the launch angle, if you look at it, his maximum angle that he was reaching was about 17.2 degrees. Now, these are the results of our actual sensitivity testing. So as you can see, there were a total amount of 17 shots played. And out of the 17, what we did is basically for whatever was practically played using the simulator, we compared by giving those same input values into our model and checking. So what we were able to figure out was that 15 times out of the 17, we were able to predict what his range was going to be within 5%. So because of that, we were able to conclude that okay, we have a confidence rate of 88%. That we can tell you confidently it's going to be within 5% of your true range for 88% of the time. And these were the key shots now that we considered. Now, because the person that we had participate was actually one of the really good, competitive, young and upcoming players. And as you saw his speed, he can hit the ball up to about 172 miles per hour. And we were talking of PGA professionals hitting at average of 108. So he's not far off from that. So because of that, and given that it was the driver, that is your first shot that you're going to play, he was giving us some very critical information on how much maximum will be reached by most of the players that are here at the ball. So if you look at this, the areas in blue have highlighted. These are the key shots that we considered because, okay, in terms of ball speed, the maximum ball speeds were clocked on shot level and 16. Launch angle, again, shot 1 and 14. And then spin rate on 3 and 8. And in red color, you can see now what I highlighted is for those shots, how much of a height was achieved at a 15-meter range. So that means 15 meters away from you, how high the ball would be. And as you can see, the one with the highest launch angle only climbed the fastest. So at least maybe climbed the shortest, right? So 20 meters was achieved at a range of 68 meters away from. Now, this is a comparison on the final after doing all our testing and all our understanding. Now, these are the values that we had used finally to derive to get to the result that we achieved. So you can see how the PGA players' values are, and then how Jacob Norton's maximum peak values were. and what kind of values we have considered for our design. And this is another representation of the swings made by Jacob, right? And then now you will see this is where the existing net is. So most of his shots is hitting at the higher area of the net, and just one of the shots of practically played at that point, he cleared the net, right? So what we proposed is that you go to an extra height and keep it at 20 meters. So then practically we are covering most of what could be hit here. And for the back tee, we propose to make a 20-meter net at a 40-meter range. So to kind of discourage the player from even trying to go through there, and maybe encourage them to go for another shot and then go in there. Now, like I said, now after all this information that I told you, you're probably wondering, okay, you still didn't understand what is going on. So what we also try to do is, okay, we are talking to people of the sport here, not talk technical expertise. So given that we actually have a 3D model, what can we do to kind of interpret this result in a way that people will understand? So that is where the 3D interpretation came in, and we got a final result file from them, basically with XYZ coordinates, and also some texture input in it as well. But we couldn't really manipulate this. Usually the 3D software we will use will be SketchUp, Revit, or something of the sort, right? So these file types are actually not openable they were not compatible. So we needed to look at another method of how we can get an intermediary software and then make a conversion and then come back to bringing them onto SketchUp. So two that we used was called Cloud Compare and Mesh Labs, right? So on the left side, you can see when I'm moving the cursor around, that is how the data is there, all XYZ points in a space, right? And then on the right side, you can see using this software, what we did is basically there are vector computations and calculations that they will do for you. And then they will calculate the normals, and after that, do vertices between the points. Basically connect it and mesh it. Like you would know into some of our software we have how we mesh it, right? So this is also similar to that. So from the first step to the second step was achieved using this software. The next challenge that we had was, okay, this file type was way too big for us to open up any of the PCs that we could use. So while consulting our architecture team, we tried to open this, tried to run it. Now using this software, okay, finally we got it converted to a version that we can use. And then that was a very new PC that we had got as well very recently when we tried to open it. And then we were wondering, okay, what's wrong, what's happening? When we looked at it, the amount of data in it is way too big. Because the one that we originally got, if you look at it, you can see at the bottom, it says vertices 3 million and faces 6 million. So usually the models, anything that we generate will never go that much, right? So because of that, we needed to do some further adjustments and kind of do some cleaning up or reducing, if you were to say, of the information that we had, of the points that we had, so that we can actually open it and manipulate the data. So using the same software, actually this was possible. And on the right side, you can see the process that was used to do this. So we targeted close to 1 million and tried it, it didn't work. And then we had target to up to about 500,000 faces to actually have it open. And then actually, so how we brought the board to the free is we have some Excel now. So what we could do is we had XYZ coordinates, right? So again, that is the very basic stage of what you would get if you were to start 3D. So we had XYZ coordinates, but we didn't have any way to really open this directly on SketchUp. So that needed some manipulation as well. Using that, we gave in the data, as you can see on your left side, it just comes as a collection of points. And using this software, we were able to mesh it. Basically calculate normals, and then after that, generate a mesh, as you can see on your right. And then you have to do some cleaning up, basically to have only the lines that had connecting the dots, so that you can make a polyline or something to start. And this is the end result. After the adjustments and the manipulation, we were able to get this open on SketchUp. Now this is a combination of the Excel XYZ that was used to do the ball trajectory, and then also using the models that we had got. So you can see that the lines and everything have distorted a bit. That is because we have reduced the number of faces that are there. But in our application, this is more than enough, and this is there to visually represent to anyone. So this is how it was originally at the front end. So if we have to tell you with the net that is there, these are simulation of that actual player who played Jacob Noah. So he's sitting at the top pins. Like we said, our design value that we recommended based on was much higher than this as well. So as you can see, there's one shot that is going over. And now we propose the solution to increase by 5 meters and clear them. And then at the back, there is no net. And as you can see with the 3D, the front nets have no impact on whatever shots are played from the back. So then we introduced a new net there. And this is how the area looked before. And this is the final recommendation. Right. With that, we would like to conclude. Thank you very much for everyone who was listening. Small few bit of acknowledgements was for Suleko, who did the 3D survey, Norton for giving us the data that actually helps us validate, and even the software that we use, SketchUp, Microsoft Excel, Cloud Compare, MeshLabs, and SPK architectural arm actually of CSEC that helped us to get to the final results and present this. Thank you all. Now I'd like to hand over to Andrea.
Thank you, Camille, for that very explanatory session on how you did the analysis and modeling. So thank you, Engineer Udula and Engineer Camille, explaining us with an introduction to the sport and the problem followed, and the modeling and analysis part as well of ball trajectory parts and to design the work nets. Thank you again to speakers for delivering such a informative session on using data-driven trajectory modeling and analysis to design golf safety nets. And I'm sure this data session provided immense value to all the participants. And it was indeed a thought-provoking and engaging session on topic of great relevance in today's sport-related constructions. We are grateful for the opportunity to collaborate with you too in our continued journey toward building a knowledge-based society. So before we start the Q&A session, I would like to remind again that the Google Form link is now open. Let me repeat, the Google Form link is now open, and it will remain open only for 20 minutes. So if you wish to receive the certificate, please go ahead and mark your attendance with the designated time. And if you experience any issues while accessing, please take a screenshot and email or WhatsApp us the issue. So with that, we can move on to the Q&A sessions. Participants, if you have any questions, you can drop them in the chat, YouTube live chat. We will direct them to the resource person and they will ask those questions for you. So we will give about 1 to 2 minutes for you to drop in the messages, and with that, we can start the Q&A session. So go on and put your questions in the live chat. Give 1 to 2 minutes.
They can ask directly.
So until the online participants dropping questions, do we have any questions from the audience? Questions? Like, wait about another minute. We have questions yet in the live chat. So seems like we do not have any questions. So with that, we can conclude the session. So thank you all the participants also for joining our webinar today. And we hope you all had a productive learning experience. Before we conclude, I have a small announcement on SDI. So as you all can see on the screen, we have a Procon course starting on the 17th of February. And it will happen for the course will be conducted for four consecutive Tuesdays from 7 p.m. to 9 p.m. So if you're interested in joining this course, flyers and the links are on our social media platforms. So you can go ahead and register for those. Register through those links. And if you have any questions regarding the course, you can always contact us from our email and the WhatsApp. So with that, we can conclude today's webinar. And if you are interested in our future webinars, upcoming courses, and our publications, then please keep an eye on our social media platforms. As you can see on the screen, we have our email, WhatsApp, LinkedIn, Facebook accounts on our social media platforms. So with that, thank you all once again for joining today's webinar, and see you next time.
What's next?
Then click on LWs එනකොට simulation එක දෙයි ඒ වගේ technology එකත් එහෙම යන එකක්ද ඒක හත්පසින්ම වෙනස්ද
ඒක basically ඒ blended camera